Okay, so this whole section is about how to model with exponentials and logarithms. So a lot of those types of things I told you, like population, half-life, financial problems with continuously compound interest, etc. Okay, so it's always good to see like, oh, I really could use this, you know? Okay, all right. These first few are not word problems. They're just practicing our solving skills and stuff, but we will work our way into word problems. Okay, so it says solve for D. So we want to get D by itself. All right. So if we're trying to isolate the D, what are you guys thinking of doing first? Yep, you bet. So we would move this guy over to the other side, which would make him negative. So by the way, let me write the steps down. Isolate all logs on one side. So that's what we're working on right now. Okay. We almost have the log isolated. How would I get rid of that too? Yeah, you could square the D, but I don't think that gives us any less with the D. That is definitely something that we could do. I think if we actually divide, it starts to isolate the D a little bit quicker, but yeah, that is the power property, yeah. Okay, so we got S minus 23, that's an ugly 3, 23.5 over 2 equals log of D. All right, isolate the all logs on one side. Condense if you need to, but in this case we only have a single log, so we don't need to. Number 3, rewrite using rewrite as an exponential using the hook. Okay, so we're going to go ahead and put our little 10 down there, and we're going to say 10 to the, what a yucky exponent, yucky. Okay, 10 to the S minus 23.5 over 2 equals, and then come back. Bam, there's your D, guys. Okay, that is not a 5. It probably looks like it. It is an S, which means that I can't actually go in here and compute that because I don't know what S is, right? Okay, but I did get D by itself, and that's what it asked for. So we're actually done on that. Okay, rewrite as an exponential, solve, and we can't really check because we didn't get a number value, so we don't have to do the check part. Okay. All right. Any questions on that one? Okay, let's try another. Solve for X. Okay, so this is not a logarithm, this is an exponential. So isolate the exponential. Good, you bet, add that T over, right? 3e to the nx equals T plus 4.2 or 4.2 plus T. Divide by 3, good. Divide by 3. You guys have totally isolated the exponential. So step 1, done. Step 2, log both sides. And we know natural log of e cancel each other out. So I will not have to use the power property on this one. But that's normally step 3. Use the power property if it applies. And now we're on the solve stage. Okay, and we're almost there, you guys. If I want to get x by itself, I got to get rid of that n, huh? Yeah, divide by n. It's hideous. Well, these sure are coming out nice and ugly there, huh? But there it is. Woo! The fraction, my fave. Okay. All right. Any questions on that one, you guys? Okay. So this is an extremely well-known formula, okay, for exponential growth or decay. So why not is going to be the initial amount of whatever. Okay, when we did that population of Mexico problem, we put the initial amount of the population of Mexico. I can't remember. I think it was 2010. Right here. Okay, so you're always going to put the initial amount right there. K is going to be the growth rate. So, or the growth constant, whatever rate, the growth constant. Okay, we know T is the time, right? Okay. And Y is the amount after T. The amount after T. Okay. T whatevers in this case. They're not necessarily years in this one. So after T passes, oops, I guess I'll say after T passes. So this should remind you of PERT, huh? Like A is the amount in the account after a certain amount of years. The principal is the initial amount. The growth constant would be your rate, etc. Okay, so this has so many applications, you guys. And all this is saying right here is if K is negative, then it's decay. If K is positive, then it's growth. Okay, so that's all we need to take from that. Okay, I'm going to write that formula down really quickly. Oh no. I might as well write PERT. Again, how did I know to write this down? Right there. Okay. All right. Suppose that at 19 years old, you win $100,000 playing the lottery. You would like to have $1 million when you retire at age 67. Determine the average rate of return under continuous compounding. So we have all these variables, right? And we want to see if we know some of them. Okay, so what do you guys think the 100,000 is? Yeah, it's the amount in the beginning. It's the initial amount. So that must make the million the amount in the end, huh? Okay. We want in the end. And you see how it says determine the rate, you guys? Determine the rate. Okay, then I don't know it. So now we just got to get the time, huh? So you're 19 years old when you start this investment, and you want the million when you're 67. So what is 67 minus 19? 48? Okay, you guys already got it. I'm just going to go with what you guys got because a bunch of you have it. All right. Okay. All right. So a little bit different than we're used to. We got different things that we know. So I'm going to put in the million over here. I'm going to put in the 100,000 that we won in the lottery. The rate's going to stay R and the t is going to be 48. So I'm going to have 48 for the time and the R is going to stay R. I switched it around, you guys, right? If I literally plugged it in, it'd be R times 48. But that's a little bit neater written 48R. Okay. So step one, isolate the exponential, right? Divide, got it. Let's see here. 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. So it looks like it's going to be a 10, you guys. Step 2, yep. Natural log both sides, very good. So we get the natural log of 10 equals 48R. You don't have to use the power property in this case. It doesn't apply, right? The e and the natural log canceled each other out. And now we're going to solve. So to solve, I guess we would divide by 48 to both sides. So Megan has 0.0479. Can I get a second on that? Yep, okay. So I'm just gonna say, let's round to 3 decimal digits. It doesn't say in the directions, so we'll just house rules 3 decimals. So that's gonna make that guy become an 8. Now, they might want it like that, but I don't know if you guys noticed on all the word problems, yeah, it gives us the percentage, right? So as a percentage, you gotta move the decimal back to the right. So he'd go right there, making it a 4.8%, which that sounds reasonable, right? 4.8% gain, okay. That's kind of cool. This is what you guys would be playing, right? You would say, let's see, I want this much when I retire, and I want to be this old when I retire. Okay, what kind of percentage rate do I need to get on my money so I can make that happen, right? That seems like something that we would all want to know. I know, not right now. Oh my gosh, they were pretty good for a while. I still get 3 or 3.5% from my school's first summer saver, but the CDs were good for a while, but now they're like under 1 last I heard. So this wouldn't be something like a CD or a savings account. If you're going to get 4.8%, then you're probably going to be investing it in the stock market, where that's normal to get something like that. Yeah. Okay, that's a little risky. Okay. According to a study published in 2012, Burmese pythons are becoming the new top predator in the Florida Everglades. Not many animals in the Everglades can stand against a python that can grow to 23 feet and weigh over 200 pounds. Scary. Oops. Sorry, you guys. Let me get my chat back up. There we go. Oh my gosh, it's huge. There it is. Okay. Scary. Okay, 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378. Write a function of the form blah, blah, blah to represent the number of pythons captured or killed 2 years after 1995. Okay, so this is going to be a two-parter in that whenever they ask you to write a formula, write a function, it's always going to be two parts. Okay, I'm just going to tell you that right now. The first part is going to be you plugging in what you know. Okay. So on this first one, plug in what you know. To solve for R. Okay. Then the second time around, once you get that, you're going to plug in P naught and R, and that's it. You're going to leave T as a variable. Leave T as a variable and leave P of T as a variable. Okay, so let me say only. Okay, and we'll talk about why in a second. I think once we do it, you might see. Okay, so done. Plug in what you know. Okay, well, let's go through here and read this. 20 Python, so P of T, you guys, the P of T part is the number of Pythons. So let me do all this stuff off to the side, okay? P of T is the number of Pythons after T years. P naught is always the initial amount of Pythons. Always the initial amount of whatever, in this case, Pythons. R is going to be the rate at which it's growing, right? And T is going to be the time in years in this case, right? Time in years. Okay. All right, so we just have to substitute all those things in. So let's see here. 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378. So we have this 20 that we have to figure out, and we have this 378. What do we think? Yeah, 20 for the, well, we got a couple P's going on right now. For the P of T or for the P naught? Yep, okay. So this is gonna be the P naught because it's the initial amount of Pythons, right? In 1995, we're considering that the beginning. So that's gonna be the initial. Then 2009, it went all the way up to 378. So that's gonna be the P of T. That's gonna be the amount after T years had passed, yeah. Okay. And then to figure out the time in this case, well, let's see here. It's 2009, right? But we started in 1995. So to see how many years passed, we had to subtract those guys. What do you guys get? 14? Yeah. Yep. Sorry, subtraction is my worst operation, so I got to stare at it for a bit. Yeah, 14. Okay. Is this me? No, this isn't you. Gonna erase your guys's. Oh, okay, you already beat me to it. Okay. Let's see here. Should I assume that's Ashlyn's daughter again? All right. Let's see here. So let's plug these things in. That's where we're at. So P of T, P naught e to the RT. Well, we got some of these things. We got P of T is 378. P naught, we said is 20. The rate we don't know, but the T we know is 14. All right, so let's go ahead and solve this, you guys. So we're gonna isolate the exponential by dividing by 20. 18.9, can I get a second on that? Okay, let's see, 378 divided by 20. Okay, yep, looks good. Okay, to get the, get rid of the e, huh? In this case, we'll just natural log both sides. So those will cancel each other out. So we have the natural log of 18.9 equals 14r. Do I want to know this growth rate for these pythons? They're going to gross me out. All right, divide by 14, divide by 14. Let's hope it's not a super big number. Okay, so natural log of 18.9 equals, and divided by 14. I'm getting 0.2099. Oof. So we said house rule, let's just do 3 decimal digits because it didn't really say. So 9 is going to round this guy up to a 10, huh? So 0.210. So if we turn it into a percentage, you is right, because if we move the decimal place twice, 21%. Not that we need to turn it into that, but it's good to know it as a percent. Yeah. There's so many things wrong with Florida, you guys. Just, you know, this is another thing to add to it. Besides having like the most murders. Now we got pythons. Okay. All right. So we're going to go ahead and take that. Oops, I got to shrink it a little bit more. There we go. We're going to plug in P naught and R, because what you're trying to do, you guys, is you're trying to create a formula to model the Python growth. And so somebody could come up to your formula, plug in any time, and see how many Pythons to expect. So that's what you want to create, a formula where somebody could go, okay, well, man, 2020, let me see if their formula worked. You know, let me plug in the time and see if it's the right amount of Pythons. So on the second one, P of T is going to stay P of T. You're only going to plug in P naught and your rate. Leave time as time, because now you have a usable formula where anybody could come up there and plug in any time they want and figure out how many pythons they can expect there to be in the Everglades. Okay. All right. I think there's a part B to this, right? Use your model to approximate the number of pythons killed in 2017. Okay, well, let me rewrite it down. Killed or captured, sorry, killed or captured. Oh, this is the killed or capture rate. This isn't the, I mean, it probably is pretty close to the actual growth rate, but this is the rate at which the number killed or captured grew. But I'm sure the amount killed or captured will grow pretty proportionally to the actual population growth. Okay, so 1995 was when we started, you guys? 1995. Okay, and it is 2017. So we're gonna have to do 2017 minus 1995. 22, yeah, good. So we're gonna go ahead and substitute 22 in for the T. So the population at 22 is gonna be the population of the captured or killed, right? Okay. So 0.21, actually I think my calculator is good enough to plug it in as is. Oh, cute number. So when you guys plug it in, Don't forget to wrap parentheses around all of that exponent. Otherwise, your calculator will just do e to the 0.21, right? So make sure you're wrapping parentheses around that. And I got to double check myself because I don't see anybody matching with me. So let me see if I did that wrong. Ugh. Okay. So there was that many pythons killed or captured, which means the population must be off the charts for people to be getting this many pythons. Now, round it, I would say round it up because you want to have a whole python. So you can't capture or kill 0.88 of a python. So you really did just kill the entire python. So let's round this up to 2030 pythons. Yeah. Wow. If that is accurate, that is a lot of pythons. Okay. All right. So creating a model, anytime somebody asks you to write the function or create a model, it's twofold. You use what you know to find the rate. And once you have the rate, you plug that and P naught into it, and that's it. You leave T as T because you want somebody to be able to plug in anytime they want and find, you know, how many of the pythons there are. Yeah, agreed. Florida, real crazy. Okay. If the ratio of pythons living in the wild to pythons captured or killed is approximately 100 to 1, how many pythons were estimated to be in the Everglades in 2012? Okay. So I know I'm going to be setting up a proportion. This tells me that. So when I set up a proportion, I like to label what I have with units here and here. So it says the ratio of pythons living in the wild to pythons captured or killed. So the top is going to be living in the wild, where you see the word 2, that's going to divide it between the top and the bottom. So this has to be the bottom. So the top is living in the wild, and the bottom is going to be captured or killed. So I'm going to put that in here. This is going to be in the wild, right? And this is going to be captured or killed. Okay. How many pythons were estimated to be in the Everglades? So do I want to know how many were in the wild, or do I want to know how many are captured or killed? So the Everglades sounds like the wild, huh? Okay. So I'm going to put an X up here, you guys, because I want to know how many were in the wild, how many were in the Everglades, okay? That means I must know this, or at least I need to find it right here. This is the ones captured or killed, right? Okay, so let me label them again. This is going to be in the wild in 2012. This is going to be captured or killed in 2012. Well, how am I going to figure out how many pythons were captured or killed in 2012? I think we created a formula for that. This is a formula that models how many pythons were captured or killed. So I just need to figure out T. So T is going to be 2012 minus 1995. So is that 17? Is that what we did before? No, it's not. We did 22 before. Okay, so 17. We're going to plug that in. Let's see what we get. 20 e to the 0.21 times 17. So go ahead and go to your calculators, you guys, and let's see what we get on that. Yeah, that's what I'm getting. Yeah, 710.33. Okay. All right. So let's go ahead and put that in right here. Okay. So now we just have to solve this proportion. We have to remind ourselves how to solve a proportion, huh? Okay. So if you have 100 over 1 equals x over 710.33.
Wouldn't it be 711 because we can't get 0.33 captured?
Yeah, I'm just not rounding. So in general, you don't round until the end to keep it more accurate. And I did 2 decimal digits because I'm noticing when I multiply by 100, it's going to move my decimal place 2 times to the right. And so I kind of like having that 0.33 there. So when this is for any math class, even chemistry or whatever, never round until you get to the final answer, you guys. Otherwise, you lose accuracy. That was a really good question, Matt, because everybody was kind of like, well, should I put 711, right? Yeah.
On our last one, though, we rounded it up because that was a final answer.
Yes.
Because you said it couldn't have been 0.33, though, right?
Yep. So if it's the final answer, you bet we're going to round. Yeah. Okay. So because I still have math to do, though, I'm not going to round them yet. But in the very end, I will. Okay, so do you guys remember how to solve a, yeah, you cross multiply. Good. So you're going to do x times 1. And you're going to do 100 times 710.33. So we might even do one more. What was after the 3? Oh, it was a 1. Let me put one more decimal digit on this, you guys. A 1, a 1, a 1. Because then that gets you on your calculator when you do the math. 71033.1. Yeah. And so because of this 0.1, I don't know. It depends on your textbook. Sometimes they have you round up because they're saying, well, that's part of a Python, so we're just going to go ahead and count a whole. I've seen them do that, which makes sense to me. So what I would do is I would just check on Connect and see if they decided to round that up or down. To me, if I've captured 0.10 of a Python or killed 0.10 of a Python, then I've actually killed a full. So it just depends on the textbook and their interpretation of what to do with that 0.1. So it could be this, or it could be this. Okay. I would accept both on that. Does that kind of make sense, you guys? Like if you were modeling the number of people that had been infected with the coronavirus, right? So if 0.1 of a person's been infected, they're still infected. So I would round that up to being 71,034. So like if I killed 0.1 of a Python, the whole Python's probably going to die. So I would round that up also. So I would say probably the better one's this one, but it's what Connect Math wants, right? And do you guys see now Matt's question, now that we played the math out, why we kept those extra decimal digits on it, you guys? Yeah, it would have given us a significantly different answer, huh? Yeah, it would have given us this. And so we would have lost some accuracy. Yeah, was it 1-1? Yeah, I'm sorry, 1-1, yeah.
I was saying to round up, though, because it should have been a whole Python that was considered in that statistic.
Yeah, and that's why I'm with you on this right here, rounding it up to a 34 would probably be the best answer. Yeah. Okay. All right. Got enough of these Pythons. Here we go. Let me see where we're at. Oh my gosh, we're almost there. I think we'll be able to finish. That's good. I always like it when we do, if we're going to do 2 sections, Thursday is the day to do it, huh? Because then it gives you the weekend. When we do 2 sections on a Tuesday, that's a tough homework to get done. So this is good. Okay. A sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. How old is the sample? Round to the nearest year. How old is the sample? Round to the nearest year. Okay. All right. So use the model for radiocarbon dating, blah, 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 where Q naught is the original quantity of carbon-14. Okay. So how old is the sample? When I read that, that tells me that T is just going to stay T, like we don't know it. So I know I'm not plugging anything in for T, okay? So that must mean that I know this and this, okay? So this is kind of a tricky one. So if you need me to explain it a few times, not a problem, okay? The fact that we have 2% of the carbon-14 still remaining, and that's the only thing that they gave me, okay? Well, I claim that that means that you just put a 0.02 on the left and get rid of the Q naught, but let me talk about why. Okay. So let's say that you didn't know how many points there were. Well, let me think of something. You didn't know how much of carbon-14 remained, but you knew that 50% was left, right? So you don't know the original amount, and you don't know how much you had in the end. Somebody just told you it was 50%. Well, I claim it doesn't matter, because let's say the initial amount was 100. Okay, so if the initial amount was 100, and it decayed, right, you have 50% left, then this should be 50, shouldn't it? If I start off with 100, then I'll end with 50. Okay, and it doesn't matter, let's say that I started off with 200, and 50% is left. Okay, then 100 of it's left, right? Now the reason why it doesn't matter is the math that we would do is, wouldn't we go and divide both sides by 100 on this? And that would get me a half over here on the left-hand side. And if I divided by 200, you guys, wouldn't that still get me a half on the left-hand side? Okay. So what I'm saying is, it doesn't matter if I know how much I started off with and how much I had in the end, you know, how much I started off with and how much I had in the end. No matter what, it's always going to get me a half over here, which is otherwise known as 0.5, right? Which is otherwise 50%. So that's why I said, whatever the percent is, you're just going to turn it into a decimal and put it on the left-hand side. I'm going to keep all this math over here so you guys can kind of try to remind yourself. Oops, let me move this junk out of the way. And now let me select it. Move it over here. Oh my. There we go. And then let's put this back. How old is this? There we go. Okay. So I don't need to know how much I had in the beginning and how much I had in the end. I know that the 2% is going to go over here on the left-hand side as a decimal, though. Make sure that you make it a decimal. Oh my. There we go. Did that make any sense, you guys? Because I can explain that one more time. So when they give you the percent, you got to change it into a decimal, and that's going to go over here on the left-hand side. Okay. And that's because for 2%, who knows how much I started with. If I started with 100 and only 2% was left, then that'd be a 2 right there, right? Okay, either or whatever. And when you divide by the 100, you're just going to get 0.02. Maybe
Question.
Yeah, go for it.
So is this kind of like our Pert's problem where the amount left over would be the 2%?
Yep.
So that would be our A, right?
Yeah. Every time. Yep. And in this case, there technically is a 1 right here, right? And so 0.02 would be 2% of 1. Okay. 0.20 would be 20%. All right. Okay. So if you get the percent, make it a decimal, put it on the left, and there's going to be your Q naught. You're not even going to worry about it. Okay. All right. So let's solve this guy. Use the model to find t. Great. Okay, so isolate the exponential. Done. What do we do after that? Got it. Get an L in here. Get an L in here. Nice, you guys. And you know these are going to cancel each other out. Beautiful. Okay. And to find the time, I guess we'll just divide by that huge, ugly decimal. Oops, not the t. Didn't too much there. Okay. So we got t equals whatever the heck that is. Yeah. What is that? Natural log of 0.02 equals divided by negative 0.1230. Yeah, that's what I'm getting, you guys. 32. I can't read it. Is that a comma? Oh my. But that makes sense because we're dating some archaeological cave paintings, right? Some cave paintings. So we do expect them to be pretty old. Yeah. Okay, I'm reading the directions and they say round to the nearest year. So I put the 0.7 there so that I would know to round up. Okay. Cool. All right. Last one, some logistic growth for us. They actually use this type of an idea for like forgeries for paintings. Like they'll be able to tell in the paint how much of some element should be in there. And if it doesn't, you know, add up, then they know, okay, somebody forged this and painted it recently. That's kind of cool. Okay. So you've heard me talk about this before. People will use exponential growth to model population growth because it's kind of good for part of it. But then exponential growth, we know, keeps going like this. So it's not really accurate in the long run. But sometimes we use models for just a limited time only. So that's fine. Okay. But if we want a more accurate representation of population growth, you know, it can't keep growing forever, right? Every ecosystem or whatever, everything has a carrying capacity. So typically you'll have a horizontal asymptote, that's your carrying capacity. So let's say the Earth could only hold, you know, so many people on it, your carrying capacity K. Well, then we should expect the population to approach that carrying capacity, right? But not go past it like this, like exponential growth does. So logistic growth is something that we use to model population growth. Got that nice carrying capacity on it. And it has two horizontal asymptotes. You can't really see it in the picture, but it's kind of sandwiched between a horizontal asymptote above and a horizontal asymptote below. If you were to graph the entire logistic growth curve. Okay. Okay. So it says Los Angeles. It's pop. Oh, did not go over well, you guys. Sorry, it's hard to read because it got the formatting's off. So it says the population of Los Angeles, P of t in millions, can be approximated by the logistic growth function, blah, 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 where t is the number of years since 1900. Evaluate P of 0 and interpret its meaning in the context of this problem. All right, so P of 0 means that we're plugging 0 in where the t was. Can you guys kind of see that? So in other words, we're saying time is 0, right? Okay. So if we're saying time is 0, when is it? T is the number of years since 1900. Okay, it's been 0 years since 1900. Oh, then it must be 1900, right? So in parentheses, I'm going to put that it's 1900. Just to remind me what I'm finding. All right, other than that, you guys, this is straight up a calculator question. Just can you use your calculator? Because that's not easy. Okay. Don't forget to wrap parentheses around the bottom if you have that type of a calculator. It might even be easiest to do a lot of this by hand, because isn't 0 times 0.052 just going to make that 0? So it's going to be 1 plus 14.589 e to the 0. And what's anything to the 0 power? Yeah. So we really have 1 plus 14.589 being multiplied by a 1. So if I actually do this by hand, it's probably going to be easier to get it to this point, right? 15.589, you guys, when you add 1 plus 14.589. And now look how easy that'll be to plug into your calculator. So I think that that would be probably better than putting that whole nasty thing in. All right, 3.194 divided by 15.589. Where does it want us to round to? Does it say on this one? It doesn't. I hate when it doesn't tell you what to round to. Okay. Now remember, this is in millions, you guys. This is in millions. So 0.204 million. So to interpret, the population of LA in 1900 was 0.204 million, right? Okay. So not even 1 million. Not even 1 million. Or 0.205. Oops, I probably should round the right way, huh? Thanks, guys. Let me make that 5 in both spots. So not even 250,000, right? So by the way, this is what, 205,000 people? Okay. So this one's probably easier to digest as far as how many people it really is. Okay. So the way I'm kind of thinking about that is 0.5 mil would be 500,000, right? And 500,000, 500,000 would be 500,000 people. So 0.25 would be even half of that, right? So that's how I was getting this number. All right. Well, still seems like a lot for 1900, huh? Like the high desert. Okay. Use this function to approximate the population of Los Angeles in 2016. Okay. Sorry, guys. I had to mute you there. Okay. All right. So let's go ahead and use this function for 2016. Okay, so I got to figure out my t. 116? Yeah, I would do 2016 minus 1900 So I'm with you on that. That's going to be 116. So we just got to plug 116 into that thing. And now I have space to write it bigger. I was still crammed on the bottom there. So 3.194 over 1 plus 14.589 e to the negative 0.052 and then plug your 116 in. Calculator time. All right, guys, let's see what we all get. So you're going to need a lot of parentheses. Don't type in 3.194 divided by 1 plus blah, 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 blah. You're going to need to wrap parentheses around the whole bottom, you guys. Otherwise, your calculator will only divide by the 1, right? The next spot where you're going to need some parentheses depending on your calculator. If you don't put parentheses around the exponent, it'll only raise e to the 0.052. So you wrap it in parentheses and hit your times button, right? So it knows to raise e to the whole thing. So lots of parentheses going on. I'm going to give you guys a minute because I don't think this was easy. Plus, I want to make sure I'm right. I mean, 3 million sounds about right, but let me see if you guys get that. Great, great, perfect. And give it a little bit longer for people who have calculators that are tough. Okay, now I want to check and see how accurate that is. Let's see what the population of Los Angeles was in 2016. So 3 million-ish is what we're getting. What was the population of Los Angeles in 2016? There would only be an estimate. Oh, okay. 3.969 million, and we got 3.086. Okay. Yeah, this is quite some time to go back to use a 1900. You know, if we went a little bit closer, we'd probably be more accurate, but it's not too bad. Okay, not too bad.